Hello. In this section, we will talk about the basic limits laws. We know the definition of the limit. We know what limit of the function means and graphically how to explain this. Now, in this section, we will try to make sure that we know how to compute explicitly the limit of the function. I mean, we need a couple of tools. Let's see. Limits laws. Yes, we have some of them here. Suppose that c is a constant, that means the value c is a constant, and limits as x is approaching a of the function f of x and g of x exist. Right? That's we have to have the limits, both of the limits exist for all of these properties. If the limits does not exist as a finite number, then we possibly have not enough information to compute I mean the other way, we will have not enough information to compute the limits, or we will need different algebra or different calculus tools. But for now, we're just focusing on the limits that they exist. Okay, property number one, the limit of the summation or subtraction of two functions is just the summation or subtraction of two limits. Yeah. Of course, f of x, g of x, x is approaching a. Limit of the constant is the constant, because constant is a horizontal line. Wherever we move, x is approaching a or x is approaching any number, any value of x, we will always get that constant. Now, property number three is the limit of the constant times the function. We may just, since we know that limit of the constant is constant, we can place this outside and focus on the limit of the main formula function, and then multiply by that constant. Number four, limit of the product is a product of two limits. Number five, limit of the quotient is the quotient of two limits. With the property number five, we have to remember denominator is not allowed to be zero. I mean, if the limit of the denominator is zero, then we do have a little bit of problem. Again, maybe not enough information to compute that type of limit, or maybe different tool will be required. Number six, limit of the power function is just the power of the limit. Limit of the nth root of the function is the nth root of that limit, knowing that the limits exist. And then, of course, we need some algebra to compute this, but that's old stuff. We know how to evaluate, how to do the algebra and arithmetic together. Okay, another important and extremely helpful property laws is the direct substitution. If the function is a polynomial or rational function at a, yes, at a also, because we will be looking at the limit at a. If the function is a polynomial or rational function and a is in the domain of the function, that's the symbol, a belongs to the domain, then we may say that the limit of the function as x is approaching a, it's the same like the value, the actual value. So we remember the solid dot, the open dot. I still would like everybody to know the difference. They are still theoretically not exactly the same. Limit means that the function is approaching that level, that value. Value f of a is the exact value, but number-wise is the same number. I mean, let's, for instance, double check the exercise that we did. Parabola, or it's supposed to touch parabola x squared. And when we investigating 3 belongs to the domain. Value of the function at 3 squared is 9. Okay? Now, limit, we know that, and when we go sufficiently close to 3 on the left and the right hand side, x will approach 3. The function will approach that red dot, or I can say this, function will approach that horizontal value, that height, that value of the function, 9. So we can say that the limit is 9. We can say that the limit of the function as x is getting closer to 3, it's equals to 9. And also the value at 3, it's 9. But we know a little bit the difference between the blue 9 and the red 9. But it is 9. I mean, that's the property. The thing is, function must be, and I didn't state this, I just say that function is a polynomial, which is defined, polynomials are defined for all of the numbers, all real numbers. A rational function, what is the common thing? Both of the functions are continuous on their domain. I mean, that was the point. If the function is continuous on domain, on its domain, on their domain. I mean, if we have continuity, because we remember when we have nice and smooth function, continuous function, then we have no gaps, no jumps, no asymptotes, and limit and the value will be the same. But we still know the meaning behind the blue notation. Okay, let's see. Exercise number 1. Oh, okay. Now, extremely basic, extremely easy. And actually, this is our question, because let's just try to compute a couple of limits of the function at the certain point, applying the basic limits laws. How function x squared behaves at 3. Yeah? Near to 3, because we know it's not necessary exactly at 3, near to 3. X squared is continuous function, that's polynomial. We can just use the direct substitution property. Substituting, getting value. Another polynomial function, how this function behaves at -2. This function is defined at -2. We can just substitute -2. Oh, a little bit lower. Doing the arithmetic, we got -10. X times square root of x, both of the functions are continuous function and they are defined at 9, direct substitution. This will be the value 27. Yeah, the height, wherever function behaves, function will approach that value, that height, 27. Okay, rational function, x squared plus 1 over 3 minus x. How this function behaves at 5? This function is defined at 5. Denominator is not 0. We can just substitute, direct substitution, and the quotient property. Doing arithmetic, we have -30. Cube root of x to the power of 5. We know that the limit of the root is the root of the limit. And in this case, we have to be smart, actually careful, because when I will do this way, if I will try to take 8 to the power of 5, because I can use direct substitution, even this way, I don't know if I can get the cube root of this number without the calculator. But we can be smart. We can put the power outside and find the cube root of 8. Everybody knows cube root of 8 too. 2 to the power of 5, 2 times 2 times 2 times 2 times 2, 32. That's we can see how we can manipulate the arithmetic and the properties. Okay. Not exercise number 2. We still, yes, just to make sure and stress that all of these limits laws are good if the limits exist, because let's see what's happened. We can only apply them. For instance, when we have a function x squared at 0, it's 0. Limit as x goes to 0 of 1 over x squared, we remember infinite limits because that's hyperbola in the first and second quadrant. And as x is getting closer to 0, the values are up. I can even draw this function, but this is just x, 1 over x squared, 1 over x squared, y, x, and we can see definitely values are going up, infinity. Okay. Infinity, we know that this is still theoretically, we can say that the limit does not exist as a finite number. But since we have some certain behavior, we're indicating this with this big numbers infinity. But now, when I will take product of this function, x squared times 1 over x squared, yes, like one function goes to 0, one function goes to the infinity. When we multiply, that's dangerous. Infinity is not existence limit. That's we are not allowed to just multiply them. Yeah, this will be not 0. And as I said before, we will need different calculus tool, or in this case, we can look where the 0 come from x squared, where the infinity come from 1 over x squared. We can do the arithmetic. We can divide, simplify x squared, it's 1, limit of the constant is the same constant, 1. So limit as x goes to 0 of 1 is 1. Okay, and we can see nothing to do. 0, infinity, and suddenly we have 1. So we have to, yes, be careful. And since we simplify this product, that means this function, x squared times 1 over x squared, this is function, when we simplify, is 1. It's just constant 1. It's just 1. But we still have to remember this function is not defined at 0. That means we will have an open dot, open circle, because we can see that that part was not defined at 0. Okay. So this is an example that the basic laws we can only apply if both of the limits exist. We can multiply, divide, taking a square root, taking a power, or any other arithmetic operation. Okay, another set. Exercise number 2. Assume that the limit as x approaches 6 of the function f of x is 4. Okay. For each part below, calculate the limit or determine that the limit does not exist. If a limit is infinity or negative infinity, let's say so. Okay. That definitely at 6, the limit exists as a finite number is 4. When we squaring, we can just say that we're computing a limit of f of x at 6, and we squaring 16. Excellent. Now we may use the property of the quotient, limit of the top value and limit of the bottom function. Limit of the constant is constant, limit of function f of x is 4, 1/4. The same for this one. Limit of x times f of x, we may split and use the product property because both of the limits exist. X is just continuous function. We can substitute 6, and limit of f of x is 4, 24. Okay, and again, limit of, we have to be careful. Okay, actually I can write this, limit of f of x as, and limit, let's see what's happened. This is 4. When we do the direct substitution, we're getting 0. 0 squared is 0. It will be just 0. And we know because as soon as we get some problem, then we have to really get back and think about the meaning definition. X is approaching 6. That means it's theoretically not exactly 6. We're using 6 as a tool, as a direct substitution property, but it's not exactly 6. It's really close to 6 on the left and on the right. I mean, if it's really close to 6, a little bit more or a little bit less, minus 6, it will be almost 0. Almost, yeah, almost 0. Like a sufficient, like a really small number. I mean, I can say small. I can say 0. Sometimes you will see 0, like let's say kind of like 0. And since it's squared, will be positive. Yeah, will be positive. Maybe I don't need this. And now this, of course, this limit does not exist. Yeah? But we also learn arithmetically, when we have a number dividing by a small number, it's a big number. Yeah? Constant, divide by 0, which 0 is considered as a small number. It's not exactly 0. Everything is positive 4, positive 0, it's positive infinity. I mean, a number, a constant dividing by small is big. Constant dividing by 0, meaning small, it's big infinity. I mean, we actually can get, but still this limit does not exist as a finite number, okay? It is infinity. We were able to do this. Okay, another one. Okay, then let's do the next one. Limit as x goes to 6 of the quotient 1 minus f of x, and denominator is actually the same like the previous one. So we will use this almost the same thing. Let's use the rules, which we probably end up not, because we can see the 0 in the denominator, but let's rewrite this. 6, and then limit as x goes to 6, x minus 6 squared. Okay, 1 minus 4, because limit of the difference is the difference of two limits. This limit of the constant 1 is 1, limit of the function f of x is 4. And now the same thing, x 6 minus 6, almost 6. That means this is small number, almost 0. Since we're squaring on both sides, it's positive. It means now we have similar situation. I can put 0, but we know it's not 0. It's a small number positive. But just like we can look at this, and we know that the constant over 0 over small number is a big number. We know that infinity will be the answer, but now just we have to make sure to adjust the arithmetic to respect the arithmetic. Negative numbers over positive numbers, of course, are negative. And we know that is infinity. It's still non-existence, but we can define the type of the limit, infinite limit. Yeah, the same thing we can. And please remember, 1 over 0, infinity. Theoretically, 1 over small number is a big number. Yeah, good to remember. Okay, and the last one on this page is we can see limit of, let me make a shortcut, limit of the numerator of f of x at 6 is 4. And now in the denominator, we have just x minus 6, which is 6 minus 6, again is 0. But now 0 as a small number, of course, small number. But now I don't know if it's positive or negative, because if the limit, yeah, if x is approaching 6 from the right-hand side, it will be 4, and that small number, oh, I wish to have more room. 6 from the right is like 6.1, 6.01, 6.0001 minus 6 will give us tiny number, small, but positive. Yeah, that means it's 4 over 0 is a big number, positive, respecting arithmetic. Now we also have to investigate the limit on the left-hand side. It will be small. Left-hand side at 6 is 5.9, 5.9, 5.999 minus 6. It's a negative small number. That means it will be negative. 4 over small 0, it's big number, but negative. Then we can definitely say that this limit does not exist as a original limit, does not exist, because it's positive, negative, infinity. We can't even state that infinity. However, these infinities are also non-existent values, because that's not a number. Yeah? We can't play with the infinity. Infinity minus infinity? No. Indeterminate form. Okay. And I have one more exercise, and we will be done with the basic laws of limits. Okay, couple of things, a small scenario, and then we will calculate limits. Now we have a function, f, g, h, I, j, k. Okay, and the function with these conditions. Limit of the function f of x and g of x at 2 is infinity. Okay. So we may guess, we remember from the previous, that if the limit is infinity at the number 2, in this case, and it's positive infinity, that means function f and function g on both sides goes to infinity, and that's the asymptote. Let's say this is f of x. G of x will be similar. Okay. Vertical asymptote at 2. Okay, function h is positive. Good to know, yes, positive, negative value, positive for all values, but not at 2. And the limit at 2 is 0. Okay, this could be also g of x. What situation we have? No value, I mean limit at 2 is 0, that's mean open dot as a limit, and values are positive. That means I don't know exactly where is the function, but must be above the x-axis, and the limit is 0. Yeah, something like this, or maybe I can draw better, like even parabola. We don't know what it is. Let's maybe even draw just parabola. Okay, now I of x, function I of x as x goes to 2 is free. Okay, that's just limits exist. I can just, we don't have to draw it. I'm just trying to picture things, like graphically explain. J of x is a polynomial. Good to know. Polynomials are defined everywhere and are nice and continuous. And the value at 2 is 5. Okay. And now we have function k of x, which is defined as a x minus 2 times j of x over x minus 2. That means function k of x is almost the same like j of x, but we do have a small requirement. Okay, and now, if possible, calculate the following limits or determine that they do not exist. Classify infinite limits if possible, positive or negative infinity, like we did in the previous problem. If there is not enough information to determine what happens, find example that illustrates the different behavior. If possible, it's supposed to be if possible. Okay, let's see. So we have this, and we will be done. Okay, the first we have to check, I will check the slides because I have to check the condition. Okay, limit at 2, I and j. Let's check. Function I was free at 2, j, we know that function is continuous and the value is given, then limit at 2 will be just the value at 2. And will be 5. It means 3 and 5. I will use this. Limit of I is 3, j is 5, the limit is 8. 3 and 5, am I? Yes. I, the limit is 3, j, for the j limit is 5. Okay, now we have a product. Limit as x is approaching 2. We can also say the limit of the product is product of two limits, 3 times 5. Perfect. Now we have a quotient, but we have h. Limit of, maybe I can rewrite this quotient. Limit as x goes to 2 of I of x, we know what it is. And limit as x goes to 2 of h. What is happening with h? Let's check. I is 3, but what about h at 2? Function, oh, we do have a problem. Limit of h at 2 was 0. Okay, but everything is positive. That means this is 0, but since the values of h near to 0 are positive, that means it's positive 0. Okay, constant over 0 over small number is a big number. Infinity, positive, it's positive. Of course, this is still not existence limit, but it's infinity. We can check it's infinity. I mean, this quotient, yes, this function at 2 will also have a vertical asymptote because we have infinite limit. Okay, now let's make a shortcut. Limit as x is approaching to I of x. The limit is, I don't have enough room, 3. F of x, what is happening with f of x? Oh, do we have f of x? Maybe oh yes, we do have f of x. Oh, I was looking. F of x and g of x goes to the infinity. I mean, okay, let's see. I will put that, but this is symbolic. Yeah, that's also, we cannot use the property directly. Yeah, this is constant free, this is big number. and constant over big number is a small number, 0. But in this case, we don't even have to know if it's like positive or negative infinity because it will approach 0 anyway. Yeah. That means it's worth to know a constant over big number over infinity is always 0. Constant over small number is a big number. Yeah. Okay, remember, that's good. Okay, 0. This limit will be 0. Okay, now we have addition. F of x, the limit of f of x as x goes to 2 is infinity. I will use that symbol. And g of x is also infinity. And we can see f of x and g of x goes up, big numbers. Now, big number plus another big number, it's even different big number. That's fine. Yeah, this is fine, which still does not exist as a finite number, but we were asked to put the infinity. Okay, now function f of x again goes to the infinity and function g of x goes to the infinity. This one we have to be extremely careful. Big number minus big number, that's the problem. In mathematics, we call that this is indeterminate form. And at this point, we have not enough information. I can say not enough information to get the limit. Okay, but the form is called indeterminate form. We have 7 indeterminate forms in mathematics. We just need more information. What is function f? What is function g? How they behave? And then we can use, again, some algebraic manipulation or different tools of calculus. But at the moment, we don't know. We can't even say it's undefined. We have just not enough information. And now, limit of f of x is infinity. Limit of g of x is infinity. And actually, big number times another big number is a big number. That's not a problem. Addition is not a problem. Multiplication is not a problem. Subtraction is a problem. Okay, and the final page of this beautiful, sweet and short session is this one. Oh, did I copy G? Okay, infinity times infinity. I can say this is infinity. Yeah, that's not a problem. Still does not exist. Or function f of x goes to the infinity as x goes to 2 and function g of x. That's another indeterminate form. Yes, this one we don't know. Dividing, yes, we don't know. That means this is indeterminate form. Yeah, we have 7. This is the second one. I mean, the second one here. And not enough information. And not enough information to get, yes, to get this, this limit. What else we have? We have a limit f of x times plus I of x. That means f of x as x goes to 2 goes to the infinity. And what was I? I was a finite number, right? 3. Okay, this will be still infinity because infinity plus like additional constant is still infinity. This is still non-existence, but we have to state infinity. This one will be infinity times 3. The same thing, infinity. Function will go up. This one is f of x, infinity, times, and h of x. What was h of x? Oh, it's the same thing? No, h, wait. Okay, h is 0. As x is approaching 2 of h of x is 0. Okay, another indeterminate form. Indeterminate form. The third one, we have 7. You will remember that we have 7. And the same thing, we don't know what kind of infinity, what kind of 0. It's not enough information. I can quickly come back. Let's look at this. I will come back here. Do you see? I didn't mention about the name and the type, but that's this 0 times infinity. And suddenly we know what functions are. We did the algebra, and we have 1. But this is indeterminate form, like the one that we just doing. And the answer could be anything. Depends on the functions, which are sitting behind 0 and infinity. Could be even 0, could be infinity, negative infinity, or the finite number, yeah, like in this case. Okay, let's come back. And k, the limit, what was the limit of k of x? What we know about k? Oh, that's a function. Let's copy the function. I mean, this will be limit as x goes to 2, x minus 2, and then k. Oh, no, that was f of x, right? Now let me check j of x. J of x. That's how function k of x was defined. Okay, j of x, product. Okay, what we have, when we substitute 2, we will actually get our favorite limit, 0 over 0. Yeah? And that's again indeterminate form. Okay, that's also indeterminate form. We have 1, 2, 3, 4 indeterminate forms. We're missing 3, but that's later. That's a different section. 0 over 0 is also the most, I mean, we talked about this, introducing limits, introducing tangent line, slope of the tangent, 0 over 0. But in case of this indeterminate form, and we do have some information. Normally, I will say we have not enough information, but we know how 0 on the top and how 0 in the denominator is defined. Looking at this, the only algebra, I mean, in this case, algebra can take place because we can cancel out the common factor, and we will end up with just j of x. And limit of j of x, did we have j here? As x goes to 2, let's check. J was 5. I mean, this limit is 5. Perfect. Yeah. Of course, 0 over 0 could be anything. Could be 0, could be infinity. But if we have common factor, if we can cancel out that 0, the 0 is gone. We remember the blue 0 is gone. And we just end up here. But again, this function 5, yes, is defined. Yeah? If this is 5 constant, yeah, we end up having function y, which is defined as a 5. It's still not defined at 2. Yeah, the limit is 5, but we do not have value. Okay, that means limit of k of x and limit of j of x is the same as 5, yeah? But not exactly the value. Yeah? Because now let's see function j of x at 2 has the value 5. That means I can put 5. Let me put this higher. This. Oh, no, wait. Oh, okay, wait, because this is 5. Okay, no. Let me, function k is not defined. Okay, that means 5, yeah. This will be, if I will draw the function j, let me use because this is 5, I will draw the entire line. I mean, this is function j of x. But function k, yes, function k of x is defined like this. And with respect to the function, I can also calculate, cancel out, but we have to be careful. They are equal everywhere, but not at 2. because this function is not defined at 2. J y equals to j of x equals to 5. That means the red curve is j. K. J is polynomial. Am I getting K? I mean, this is true for all of the x's except 2. So we can see green line, red line, the same. Green line, red line. This is different. K has an open circle because we can see function K is not defined at 2. Even if I cancel out, that's later steps, but it's not defined at 2. That means K has the open circle, J has the entire line. Yeah? In this situation. Yeah? And actually, I think we answered the last part, true or false. K of x equals to J of x for all x's. No, not for all except 2. And that means they are equal for all of the x's, but not at 2. At 2 is different situation. Open circle, yeah, no value for K, value for J, the green dot. Okay, enjoy your basic laws of limits. Thank you.